Okay, in this presentation we are going to look at continuous probability distributions, specifically the maxima and minima, the distribution of maxima and minima of paired random variables. So we have a continuous random variable here, x, and it has the following probability density function. F of x equals 1 over 2 theta for x between minus theta and plus theta. Okay, in fact, usually these definitions are going to be from minus theta to theta the whole way through. So I'm just going to skip over that part for the sake of brevity until I need it. So we've got a couple of exercises here. Show that the cumulative distribution function of x is f of x equals x theta plus x divided by 2 theta, again between minus theta and plus theta. Deduce an expression for x greater than x, okay, which is the complement of the distribution function. The random variable y has the same distribution as x and is independent of x, okay. The random variable z is defined as the maximum of x and y. So show that the cumulative distribution function of z equals theta plus z divided by 2 theta to be squared for z between minus theta and theta. Deduce an expression for the CDF of z and hence find the expected value of z. Okay. One more. There's two more in fact. The random variable w is defined as the minimum of x and y. Show that the cumulative distribution function is as follows. Theta minus w divided by 2 theta to be squared for w between minus theta and theta. Again, find the probability density function of w and the expected value of w. Okay. Find the value of the constant k such that the expected value of k times z minus w is theta. Okay, now there's a lot actually in this, and I'm going to go through it fairly quickly. But just to remark that there's a couple of key points here to remember. So I'm assuming that if you have got to the stage where you're studying this in a course, that you'll probably be familiar with some of the fundamentals. So I'm just going to sort of state them and move on. Okay, so the cumulative distribution function of x and probability of x greater than x. Okay, so the complement of the cumulative distribution function. So essentially what we're given here is the probability density function, f of x equals 1 over 2 theta from minus theta to theta. Okay, so the cumulative distribution function, capital F of x, is found by integrating that from the lower bound to x. Okay, now this is a point where the lower bound is important. So the lower bound there is the range of values which supports x minus theta to theta. Okay, so capital F of x equals the integral from minus theta to x of 1 divided by 2 theta dt. Okay, and we will evaluate, we just use this sort of dummy variable for the time being. So here we're just going to use t because we're not using it anywhere else. Okay, so evaluating the integral, f of x equals 1 divided by 2 theta, which is a constant as in t, our dummy variable. So you have this integral from minus theta to x of 1 dt. Okay, so the integral of 1 dt is t. Okay, so you have 1 divided by 2 theta, and we have a definite integral from t to evaluate it between minus theta and x. Okay, so f of x equals 1 divided by 2 theta times x minus theta, which is theta plus x divided by 2 theta. Okay, so that's the cumulative distribution function of x. Okay, straightforward enough. That's using the definitions, okay, of the probability density function and its relationship to the cumulative distribution function. In fact, a bit long-winded, but nothing really dramatic there, just a sort of a statement of what we should be familiar with. Okay, so the cumulative distribution function is theta plus x divided by 2 theta for x between minus theta and theta. Perfect. And to find the probability of x greater than x, that is simply the complement of the cumulative distribution function, which is 1 minus theta plus x divided by 2 theta. Okay, so we express 1 as 2 theta divided by 2 theta. Okay, and just simplify it. So we have 2 theta minus theta plus x divided by 2 theta, and that gives us theta minus x divided by 2 theta. Just watch out for those brackets there. Okay, so let's just take a moment to absorb that. I don't want to be too fast, but we have a lot of work to get through, so I'll keep moving. Okay, Now, the distribution of z, which is the maximum of x and y. Now, given that x and y are independent and identically distributed, i.e. deriving variables, with the same distribution, and z is the maximum of x and y. Okay. Now, requires a bit of guile here, and because there's one coming up there where we ask about the minimum, this sort of comes in twice. Okay. Now, this is the key part here. It's the first and second line of this equation array. So the cumulative distribution of z is the probability of z less than some value z, okay? Now, z is defined as the maximum of x and y. So probability of x and y is less than z is what we're asked for here, okay? Now, the second and third step is important. This is the sort of where you win here, okay? So if x is less than z, and y is less than z, and the maximum of x and y is less than z, essentially what you can say is the probability this is equal to the probability of x less than z and y less than z, okay? So that second to third line there, the step between the two, just keep it simple in your mind. Don't overthink it, okay? So if the maximum of two values is less than a certain threshold, that means they're both less than that threshold. And that's all you have to think about, okay? And don't try and overthink it. So literally the second to third line there is essentially all you need to do, and don't try and overthink it. Just remember that's the key part of working with these maximum and minimum problems. Okay, so the probability of x less than or equal to z and y less than or equal to z, these are independent events. So essentially what we have here is the probability of x less than or equal to z times the probability of y less than or equal to z. Okay, and in both cases they're sort of equal to each other. Remember that we were told that their x and y are pretty much the same. So essentially what we have here is probability of x z squared with f of x, f subscript x of z squared. Sorry, there was a bit of a tongue twister there. Okay, so that's the cumulative distribution function for variable x evaluated at z, which is also the same as it is for y, okay? And that is theta plus z divided by 2 theta squared. Again, the squaring comes from the fact that we were doing it for x variable and for y variable, okay? So that is our answer there, theta plus z divided by 2 theta to be squared, okay? So the next step here is calculate the probability density function. And this is straightforward enough, really. In fact, it's just to do a quick take on it and move on. So the relationship of the cumulative distribution function and the probability density function. To find the probability density function, essentially what we do is differentiate the cumulative distribution function, okay, with respect to z. So f of z is the derivative with respect to z of the cumulative distribution function of z, capital F of z, okay, and that is ddz of theta plus z divided by 2 theta squared, okay. Now I'm going to sort of just recall down to, or draw your attention down to the bottom there. That's just essentially an expression in z squared, okay. So essentially what we're going to do here is just recall the chain rule. Okay, and that's how we solve that. It's straightforward enough, really. It looks a little bit complicated, but just recall the chain rule. That's all we have to do. That is 2 times theta plus z divided by 2 theta times 1 over 2 theta. Okay, so it's that's it, yeah. I'm not going to go into it anymore there. So just evaluate that. We have theta plus z divided by 2 theta squared. And that's us done there. Okay. Likewise, the expected value of z is the integral from minus theta to theta of z times the probability density function. Okay. So we have an expression there that is 1 over 2 theta squared. So we're just going to sort of separate add that out because it is constant. So we have 1 over 2 theta squared times the integral from minus theta to theta of z times theta plus z dz. Okay. So what we can do is split that integral up. Okay, so we have 1 over 2 theta times theta of the integral of z dz plus the integral of z squared dz. Okay, and that's a symmetric even function. So the integral of that from minus theta to theta is simply 0. So the integral of z squared dz when evaluated from minus theta to theta is z squared divided by 3 evaluated from minus theta to theta. So that's theta cubed divided by 3 minus theta cubed divided by 3, which is 2 theta cubed divided by 3. So the expected value of z is 1 divided by 2 theta squared. Okay, remember, just going back a bit, we took that out at the start there. Just see that third line there. Just remember that has to be brought back in. Times 2 theta cubed divided by 3. So that ends up as 2 theta cubed divided by 6 theta squared, which works out to be theta cubed. Or theta divided by 3, sorry. Okay, so that's the expected value of z. Now, I'm going to sort of run through this part here very quickly because I don't want to overstay my welcome. The distribution of w is the minimum of x and y. So essentially what we're going to do here is just recall some key definitions. So the cumulative distribution of w is the probability of w is less than or equal to some value w. And that is equal to 1 minus the probability of w being greater than some value w. Okay, so that's just the sort of general sense of what a cumulative distribution function is about. Okay, so if w is the minimum of x and y, essentially what we can do is what we can say is that is equal to 1 minus the probability of min of x and y greater than w. Okay, and just like we did before, we can re-express that as 1 minus the probability of x greater than w and y greater than w. Okay, and these are independent events, so what we could say is that is 1 minus the probability of x greater than w times the probability of y greater than w, and that's using an expression that we found previously. So what we have here is 1 minus theta minus w divided by 2 theta squared. Okay, so it is going from the, just recalling those definitions and sort of going from that bottom equation array, going from the first line to the second line. That's the trick there. Don't overthink it. Just over to say if the minimum is greater than this, that means they're both greater than this value. Okay, and they're independent, so you just sort of separate them out. So again, to find the probability density function, we take the derivative of the cumulative distribution function, and again, this is using the chain rule. Okay, we have 1 minus theta minus w divided by 2 theta to be squared. Okay, so this is a very same sort of setup there. Essentially, we have minus 2 times theta divided by minus theta minus w divided by 2 theta times 1 minus 1 divided by 2 theta, and that is theta minus w divided by 2 theta squared. Okay, nothing really amazing there at all. That's the chain rule, so that's all we're doing. Differentiation, chain rule, just sort it out and move on. The expected value of w is the integral of w times the probability density function. And again, this works out almost the exact same as the last time. And I'm going to just glance over a bit, just to sort of say, we take out that term 1 divided by 2 theta squared. We split up the integrals into two parts. We have the integral of w dw and the integral of w squared dw. And again, one of them, the first term, will evaluate to 0. The second term will evaluate to 2 theta cubed divided by 3. So we end up with the expected value of w equals 1 divided by 2 theta squared times theta times 0 minus 2 theta cubed divided by 3. Okay, we end up with minus 1 divided by 2 theta squared times 2 theta cubed divided by 3, which is minus theta divided by 3. Okay, and finally, so we have got to find this here. Expected value of k times z minus w, let that equal to 0. So what we do here is substitute in the expected values found in b and c, which they are there, and just try and solve it there. So we have the expected value z minus expected value of w. That is 2 theta divided by 3 minus theta divided by 3, and that is let that equal to theta. Okay, so we have k times theta equals theta. That means k equals 1. Okay.